Hi, and welcome to the Special Situations cast. My name is Bram de Haas. I run the Special Situations report, which you can find on Seeking Alpha. Before we jump into the interview with my guest of today, I want to make a few things clear. Nothing on this show is investment advice. It's for entertainment purposes. Either me or my guest may have positions in any stocks or securities that we discuss. So keep that in mind, and please go and enjoy my interview of today. Welcome to the Special Situations cast. Today I have a very special guest, Philip Freidin. Welcome, Philip.
Good morning or good afternoon. The name is actually Freidin.
Freidin?
That's okay. Yeah, that's okay. I mispronounce it sometimes as well. Hi. So,
Hi. Yeah, it's my Dutch background. It's a little bit like German, and that's how I mishandle that.
That's okay. I'm used to it being mispronounced. It's happened my whole life.
Oh.
So thank you very much for inviting me to talk to you. I'm a guy that's worked in engineering for about close on 45 years, and the last 35 of which I've worked in Silicon Valley. I worked for Advanced Micro Devices as a CPU architect. That's somebody who actually defines a product based on the prediction of what customers will want. And I worked on the very first generation of RISC CPUs and bit-slice CPUs at AMD. I then worked at Xilinx for 5 years as an employee and 10 more years as a consultant, performing a similar role of defining products. And I joined Xilinx only a few years after it started, so I joined Xilinx before it went public and continued working with the company all the way into the early 2000s, doing the product development and definition for FPGAs. And then after Xilinx, I became a consultant, and I worked with various silicon companies doing product definition, and I also worked for end users designing FPGAs into their products. And one of the great things about working in Silicon Valley is there is just a huge number of interesting companies, and I worked on everything from satellite communications to ultrasound imaging for medical applications. Okay, so that's my background.
Thank you so much for the introduction. I'm so excited to talk to you. I think you're the perfect person for this. I actually invited you because of the potential acquisition of Xilinx by AMD. And a lot of people are very interested in that possible event. And well, the way I understood it is that the FPGAs that Xilinx makes are like a core reason that AMD likely wants to do this. And I mean, you know everything about FPGAs, and maybe you can tell us what are they great at and what are they not so great for?
Sure. Certainly AMD's interest in FPGAs would be the only reason for acquiring Xilinx, since that's all Xilinx does. I think the best way to explain what an FPGA is, at least from a very I guess I would call it a non-technical point of view, is maybe explain it in something that you almost certainly do have a good handle on. So you have a desktop computer in front of you, and when you first turn it on, it doesn't know what's going on at all, and it takes a few minutes for your computer to wake up and loads software off the disk, which we typically call an operating system. And then, it paints the screen with an image, and then you choose from a very long list of possible programs a program you want to run. So it might be an Excel spreadsheet, or it might be a word processor, or whatever, or a browser, right? Go look at the news, right? So you have these different programs that come from different companies, and they let your computer behave totally differently depending which program you load, right? And the good news is that you aren't stuck with whatever the initial programs were that were available at the time you bought your computer. There are always new programs coming out and updates, and you can always, depending on the company, either get a free update, or maybe you have to pay for it, or you buy some new program that gives your computer a new capability that you didn't have previously. So that's how a computer works. An FPGA is somewhat similar in that when it gets shipped out of the factory, it has no idea of how it's going to be used, right? There are lots of different sizes of FPGAs, and they have different sets of capabilities, but it isn't until an engineer starts doing a design that includes an FPGA that it might start to have some particular functionality. And that functionality could be something like a DSL modem, or a video converter, or the control system for a satellite, or an ultrasound machine, or pretty much anything that isn't an extremely high volume product. So if you talk about something like a cell phone, right, a smartphone, or anything where you're shipping them in the millions, then FPGAs typically don't get used because they're too expensive. But in something where the volumes aren't quite that high, anything from hundreds of something up into the hundred thousands, FPGAs may be the right product to implement it. It also depends on what the problem is you're trying to solve. Like a processor in your desktop computer, the way the FPGA gets woken up is similar, right? You talk about booting a computer, that's the name given for the process of loading the operating system. So there's a boot process for an FPGA which loads up the software from some type of storage, and that then makes it behave a certain way. It is in this regard that FPGAs are different than pretty much every other type of product on the market other than CPU chips. So CPU chips, everybody knows that they can do different things depending what software you load. Pretty much every other type of chip is fixed function. It's a memory chip, it's a communications chip, it's something that knows how to multiply and divide, right? Whatever, but they're all fixed functions. But the FPGA isn't. Like a processor, depending what the boot software is, software is the wrong term, but let's just stick with that for the moment. Depending what information the product boots up with, it will behave differently. And so a company that makes FPGAs, of which Xilinx is the leading company and has been for more than a decade, basically the engineer looks at the level of complexity of the product they're trying to build. So if you're building a toaster oven, probably not a great example, but if someone's building a toaster oven versus someone is building a medical ultrasound machine, it's pretty easy to guess that the ultrasound machine needs far more complex calculations, right, than a toaster oven, right? And so you might pick a different size FPGA. Well, you absolutely would pick a different one. But the actual internals of the FPGA would be the same, other than how much of the FPGA stuff is in the chip. So for the toaster oven, you pick a very small FPGA. For the ultrasound machine, you'd pick a very big one, right? But it's just a matter of just how much stuff there is. It's like how much memory there is on
So,
your computer.
Philip, if I can
Yeah,
summarize this like from a non-technical background, I don't know anything about chips, and they will never get into things like laptops or desktops because those are go by the millions. But
right.
if somebody has a product line that needs computing power or memory, um, and it won't make like a huge amount of it, then FPGAs are actually really cost efficient.
That's absolutely true. It's, I guess there is one area where FPGAs might show up in a desktop computer, probably not in a laptop, or at least not in any normal sense.
They're also a
And that
little bit
is,
bigger, right, in size.
um, I don't, not so much size, it's the typical workload that you run on a laptop and the level of expansion you do. So if you look at your desktop computer, you may rather, while there might be video capability built into the main board of your desktop computer, companies like NVIDIA and ATI, which got acquired by AMD, right, make video cards that are quite expensive and are an add-on to the computer, and not everybody uses them. But for
Yeah.
those people who want, excellent graphics on their computer, they will pay extra money for an add-on board. And so there are
Right.
add-on boards for computers that have FPGAs on them, right?
Right.
And they are specifically for accelerating some type of computational operation.
Yeah, and that's a graphics card, but what I'm hearing is that that's also what it's used for artificial intelligence.
Yeah, so the calculations that are needed for doing AI training is the same type of calculations that happen to be what graphics cards already know how to do. And so people do in fact use the very high performance graphics processors, GPUs, for AI training type applications. And they also use FPGAs for that as well.
And then something that I don't really grasp yet is I understand that FPGAs could be interesting in data centers.
Yes.
I don't understand how that jives with what you just said, that they're not great as a like a mass-produced item, because data
Okay.
centers, it seems like mass production.
Okay, so those actually are, but those are in the millions rather than hundreds of millions. So the if you think about a data center is your desktop computer, right, multiplied by millions, right, all put in one place. And I guess the major feature of a data center is the external companies that use them, get to only buy as much resource as they need. And the whole problem of managing the data center, repairing things when they fail, doing backups, is now a problem that the end customers no longer care about because the data center company provides it. So so let's say you have some sort of application which needs 1,000 servers, right? Rather than having to go buy yourself an IT department and fill it full of servers, you instead contract with Amazon Web Services, right? And you basically make use of 1,000 of their servers, and you don't have to worry about if a server fails, Amazon takes care of it. If a disk drive fails, Amazon takes care of it, right? So all the management problem is taken care of by Amazon. But more importantly, let's say you announce a new product and suddenly the amount of hits on your website doubles overnight, right? And you now don't need 1,000 servers for all your web traffic. You suddenly need 2,000. Well, if you had your own IT department, they'd say, come back in a year and we'll be ready for you, right? With Amazon Web Services, you type a command in and suddenly you now have double the number of servers, okay? So the servers are general purpose versions shared versions of what your desktop computer is, right? And there are computational workloads like AI training where FPGAs are exceptionally good at it. So are GPU chips. And so the web services companies like Amazon, but there are others. There's Baidu, there's Google has web servers,
Microsoft.
Microsoft Azure, and Alibaba, I believe, also provides massive web servers. So there's probably more, I mean, this is not my area of expertise, but I know of at least 6 web server companies that have millions of servers. And so starting a few years ago, maybe 4 or 5 years ago, they recognized that FPGAs for some applications can be 100 times or 1,000 times better performance than a normal CPU. And so they started building parts of their web services where they added the resource of FPGAs. So when you get access to a server from Amazon Web Services, they aren't all the same. Some of them have more memory, some of them have more disk, some have more communication capability, and you pay different amounts of money based on how many servers you have and what the capabilities are of each one. And you can mix and match. And so Amazon now has servers that have FPGAs built in. And so when
if I can interject for a second,
sure,
because mine is blown. So they're really flexible, but in some tasks they're also super high performance.
That's the only reason you use them, right? Because if all you wanted was flexible, CPUs already give you that, right? You just load a different workload, right? Or send it, or tell one of Amazon's web servers or services box, right, to run a different workload, right? So that flexibility already exists in CPUs. The reason you use FPGAs is because FPGAs let you build a processor, right? The actual compute part of a computer is called a processor. It lets you build a custom version tuned only to do the problem you want to do, but do it stunningly better. And I've looked at your question list. We're going to get to where you ask me a bit more detail about how FPGAs are different, and I'll dig in there to sort of explain. Actually, maybe I'll just do that now. So if for your typical desktop computer, even the most general user probably knows they care about how much memory they have, right? So let me play the game. How much memory is on your computer in front of you?
Oh, I don't know, maybe 16.
16 gigabytes probably.
Yeah.
Right? Okay. And you probably have a disk.
Yeah.
Okay. Do you know how big it is? Okay, well, it's probably a few hundred gigabytes, and there's probably a processor in it, almost certainly from Intel or AMD, right? And it probably has a performance level which is some number of gigahertz, right? So that says how fast that processor can do operations. So if you have a processor that is a 1 gigahertz processor, which now would be pretty old technology, then that means, so 1 gigahertz, that's frequency, like you talk about. The most recent stuff is there's this 5G radio, which happens to operate in several bands, but one of them is 5 gigahertz. So hertz is cycles per second, if you want to sort of get its origins before it got the word hertz added to it. So a gigahertz is 1 billion operations a second. So those billion operations might be add operations. So it can add 1 billion numbers in a second, right? Multiplies take longer. Maybe it only does 1/4 billion operations if an operation is a multiply, right? So, when you design processor chips, you do various trade-offs of that sort of stuff. But in the end, the processor can only execute, that's the term we use for actually doing an operation, one operation after another. Now, the actual speed of processors pretty much stopped being improved about 5 to 10 years ago. It pretty much hit an upper ceiling of about 4 billion operations a second. And so what we started to see was, instead of going faster, because they couldn't, they started adding more and more cores. And so we now hear about processors with 4 cores or 8 cores or 16 cores. And that just means that there's effectively 16 computers each. If you had a 16-core processor running at 4 gigahertz, it means you've got 16 separate processors, each running at 4 gigahertz. Now, when you're browsing a website on your grossly overpowered desktop computer, only one of those processors is doing anything.
Okay.
Right? The rest of them are sitting idle because the actual program itself has only one task, which is paint a web page onto your screen. Right? There is no opportunity to make use of the other cores in your processor. Right? So
yeah, they
go ahead.
refer to that as like single thread or something, eh?
Right, exactly, right? So there's some little bit of stuff that you can try and use other threads, and if you have multiple cores, those threads might run on different cores concurrently. So, a really top of the line desktop computer might have from 8 to 16 cores. Right? 16 cores would be the very top end of desktop computers, which actually tend to be gaming systems.
Yeah.
Okay. And for that, we actually start to see an application where those extra cores are useful, and that's in very high-speed graphics. And this is also something GPUs do as well, and that is the single thread of something like a word processor or a web browser is because there just isn't much you can do concurrently, right? You're waiting for stuff to come over your internet connection.
Maybe play music or...
right, so yeah, you might have a thread to play music.
Some data importing.
Right, or you might have some programs running in the background, updating your stock ticker or something, right? But none of those are particularly computationally problematic. But graphics, putting up a real-time game display is very computationally intensive. And the thing that is different about that workload versus an editor or a browser is that you can partition the problem into a lot of separate problems that can run concurrently. So the problem is, if you look at an image on a screen, it's made up of these little things called pixels, right? And each one of those has a color, right? It takes calculation to figure out what color each pixel is. And the color of each pixel is totally independent of all the ones around it, right? So you have more than 1 million pixels on the screen. Each one has to be calculated. So if you calculate them one at a time, you have to do 1 million calculations one after the other, right, for a 1 million pixel picture. But if you have multiple cores, you can calculate 16 pixels at a time, for instance, and then do the next 16, and then do the next 16. And you still have to do the same 1 million calculations, but you get the result in 1/16 of the time, right? If you look at the graphics processor chips, the GPUs, some of those have over 1,000 cores in them. And that lets them do 1,000 calculations concurrently.
And that becomes really important when things are moving and there's like lights that are reflecting.
So if I look at the background for your image and my image, 95% of that image isn't changing, right? You've got a very white background. I've got a more mixed background, but none of those pixels change. And so there are tricks you can do in your graphics processor to recognize regions that aren't changing, and they can avoid doing the calculation. Whereas watching your head move, watching my head move, my lips move, those pixels are changing all the time. And so it definitely is having to recalculate that, not just once a second, but like 60 times a second, right? So that our image is not very, right? So our image is, moves evenly. It's not jerky, right? If I
Yeah.
put my hand up and I move it slowly, you'll see a little bit of an error on the edge of my fingers, but the bulk of the way it shows my fingers is correct. But if I move my hand quickly, right, the pixels are a mess, and that's because it can't keep up,
Right. And so,
right?
so I think what I understand in gaming is that the hardware has been like the limiting
Right.
factor in making
Yeah,
it
and
as
and
real
it's
as
actually the
possible.
graphics. It's the graphics part of running gaming, is that you're trying to create. The term is photorealistic, would be
Hmm.
ideal, but photorealism is still beyond most graphics hardware, right? So what we get is very high resolution, but it still looks, I guess I would say the coloring is more artificial. I guess there's just something about when you look at a real scene that you have the detail. Good examples are hair, right? Or, someone's got more hair than me and they swing their head and the hair moves, right? That requires, every single hair is a whole bunch of pixels on the screen. Each one has to deal with the motion that's a little bit different,
Yeah.
right?
In animation, it's also one of the great challenges.
Right. So, the computer games went from stick figures, right, to very simple comic-like stuff, to, the stuff we have now, which we're very familiar with seeing from Pixar movies, where you can still see that it's not real, but it has shading and lighting direction and casting of shadows, and they aim towards eventually getting what they call photorealism, which
Yeah.
is you can't tell the difference between the scenery and a photo of the scenery,
Yeah.
right? And then you need to be able to, so you can do photorealistic images, but you can't do moving photorealistic images, right?
And
Because it
maybe
takes too much compute.
I'm getting a little bit sidetracked, but
Yeah, sure.
maybe have you ever tried one of those Oculus type
Yes, I have.
headsets?
I've played with. There was one, not Oculus, but one of the competitors to that was something called Cast AR, which was, again, it was actually an augmented reality rather than virtual reality. So it actually overlaid an image over the scenery in front of you, right? And that company ended up. They folded, but the technology moved on to a new company called Tilt 5. And so I played with their headsets during the early development phase, because they were using FPGAs and I knew the lead developer. So we
Also,
talked about some of this stuff. And yeah, that's an excellent example of where real-time motion is critical, right? Uh, because if it's not real time and updating very close to when it occurs, you get all sorts of nausea problems, etc., that have been reported for some of these virtual reality headsets.
yeah, then it's not a great experience. But when I tried it, I was amazed that I don't think that doesn't need to be like super realistic. But if it
Right.
just gives you that experience of reacting, then
Hmm.
um,
Yeah.
it should
So
be real.
right. So
Uh,
that's another good example where parallel computing, which is the general term for this, right? The more the more computing you can throw at the problem, the better the realism of the image and the faster the updates occur, right? Which lets you get from thinking you're looking at a cartoon to, getting more and more realism. Anyway, let's drag it back to FPGAs, since
sure,
we were
and
talking about that.
but my last comment is that
Yeah,
so you used FPGAs when you were building like a prototype or something for a VR company, and that's like an ideal
right.
type of situation for a FPGA if you're building prototypes.
Okay, so sure, we can talk about that. By the way, I was not actually involved in the development,
Oh, sorry.
right? But I knew the developer, and we were friends, so we talked about it. So since the very earliest days, FPGAs have been used by people who are building custom chips. They've used FPGAs to prototype them because it's a safer, cheaper way to do stuff. And that's still true today. You build a custom chip if it's going to go into very high volume, and the threshold of where you change over from using the FPGA to using a custom chip depends on what your volume will be and how expensive it is to develop that custom chip, right? When I joined Xilinx in 1989, the crossover point was probably at around 1,000 chips, right? So if you're going to build more than 1,000 of something, then you might prototype with FPGAs and go to production with a custom chip. And that was because the cost to do a custom chip back in that time frame wasn't particularly outrageous. It might cost you $100,000 to develop a custom chip, which you could then amortize over a few thousand, or if you amortize over 1,000 chips, that's $100 per chip. So maybe 1,000 is too small a number, but at 10,000 chips, now it's only a $10 load per chip. And so, if it's a chip that sells for $20 and 10 of that is for development, that's a more reasonable calculation. And as your volume goes up, that $100,000 becomes more and more irrelevant. Okay. These days, the cost to develop high-end custom chips can run into the hundreds of millions of dollars. And so the actual crossover point between where a custom chip makes sense over an FPGA has actually moved up year by year. And so for many applications, even if you're making 1 million of something, the FPGA is still the right choice. Right.
And
So yeah,
do you
I'd
think
like
that
to at
inflation
least,
continues?
no, it's so what's happened is the cost of developing leading edge products has continued to go up,
Right.
right? And that's because those microns kept getting smaller and smaller, and then they became nanometers, right? And so now they're down around, 7 nanometers is the current level that the best fabs boast about. So while that lets you build much smaller chips, the cost of developing the design for those chips and taking them to production has continued to go up, right? So it's kind of counterintuitive that although the chips themselves can be much cheaper for the actual piece of silicon,
Yeah.
right, that because they've shrunk, the actual cost to make them has become astronomical. So you've got to have very, very high production quantities to warrant building custom chips.
Yeah, what I meant to ask is like, do you think that convergence continues in this direction? That the
Oh yeah,
bar,
absolutely.
yeah.
Yeah. So
So
that will continue. The other thing is that the FPGA companies, not just Xilinx, but Xilinx, Altera, and others, have recognized that there are some things. We're going to be talking about how the FPGAs are very, very flexible, but there are some things you can recognize that don't need to be as flexible as what FPGAs can typically achieve. And the flexibility which we'll be talking about comes at a price, and that is it requires a lot more silicon to make something flexible, right, than not flexible. So if there's something that doesn't need to be flexible, then you can pre-build it using more traditional non-FPGA techniques, but included on the FPGA chip. Right. So, for instance, we talked about graphics. So the primary calculation that GPUs do, there's only two operations. It's multiply and add. Right. They are the dominant calculation that GPU chips do, and so FPGAs have something called a DSP unit, and what it does is multiply and add. And rather than make it ultra flexible, which is how FPGAs originally did it, right? Once we recognized that this was a common requirement, we then built multiply and add units pre-built into the FPGA. And when you do that, they run faster and they're 1/10 the size, so you can have 10 times as many of them. So it wins in cost, because it's 1/10 the size. It wins in performance because the flexibility does affect performance. And when you take away the flexibility, it runs faster. And so pretty much all the FPGAs that Xilinx and Altera do now have hundreds or thousands of these blocks that do multiply and add.
Yeah, makes total sense if you hear it now, but it was probably breakthrough when
30 years ago, when I was architecting FPGAs, the fights I had to go through as an employee at Xilinx to get them. So I was actually the guy that, quote, invented adding multiply and add functions as pre-designed parts of FPGAs, and the other one was blocks of memory. Right before I came along, there was some very limited memory in FPGAs, and again, it was an interesting internal battle at Xilinx to see that the future needed to have blocks of memory. And now pretty much all FPGAs have blocks of memory in them and these multiply add blocks. And then the third one, and again I actually championed this, was adding processors on chip. And so Xilinx has processors in their Zinc product line and several of their other product lines, and so does Altera, right? And these processors, they've actually tried several different types, but everybody has now settled on ARM CPUs. No, that's not true. Not everybody, but most companies have chosen ARM as the appropriate on-chip CPU. And again,
maybe the others are going to.
Well, they will eventually figure it out. But yeah, certainly Altera and Xilinx both use ARM CPUs as their primary one. But Xilinx initially tried using something called PowerPC from IBM. And that was one of the projects. I wasn't directly involved in that decision, but I worked on that product as a consultant, working on the memory and the multipliers. So, you know, I had some close watching of that evolve. So, you know, all three of those, right? The arithmetic section, the memory section, and the processor are now all built into the FPGAs, but as the correct term is hard blocks, and they call them hard just because they've lost the total flexibility that the FPGA has elsewhere, which is where we still have to go talk about, you know, what makes FPGAs different from a CPU chip.
Right. I think we're going back to that at the end, right?
Well, actually, we're going to come up to it anyway when we talk about where are FPGAs well suited to.
Oh, right. Okay. Let's go through that. What are they great for?
So let me give you. So we talked a little bit about pixels, right? Which is kind of abstract since most people don't think about pixels as part of their normal, you know, compute problem. So let's pick something that is obvious. Let's say you have a document, a huge document that has 1 billion words in it. Okay.
That is very common for me.
A billion words? Probably not. A billion words is more than a library, right? But let's say you have a billion word document, right? And you have to spell check it. Okay, so let's think about what is involved to spell check a word.
My editor.
Right? You take, well, so let's say you didn't have a computer in front of you, but you had a dictionary in front of you. So the first thing you have to do is take the word, and hopefully your dictionary is sorted, right? Right? The dictionary is sorted a very special way called alphabetical, right? And so you have your word in front of you, and if you're lucky, the first letter of the word is a letter you recognize, and your dictionary has tabs on it from A to Z, which gets you close, right? So you do an initial dive into your dictionary by jumping somewhere, right, close to where the word might be.
I'm
Right?
old enough that I've gone through this process.
Right, okay. And so anyway, so you do that, and then you flip pages backwards and forwards, scanning all the words in that locality, eventually either finding your word or not finding your word, right? And if the first letter is wrong, then you don't have any hope at all,
No.
right? Because there is no way to search a dictionary where you don't know the first letter is correct, right?
Yeah. Only a
But if
very
you do a
slow
spell
method.
check on your computer, it can do that. So clearly your computer has a spell check capability that is smarter than the typical dictionary, right? So there's an interesting thing to just notice, that computerizing the dictionary search, you can do things that you could never do with a book. Okay, so anyway, you dig through the dictionary and you find your word is okay. Great. Let's move on to the second word. Guess what? None of the work we've done so far affects how we search for the second word, right? We're back to the beginning and we repeat the operation.
Yeah.
The thing I want to emphasize is the search for the second word is totally independent of the result of the first search. It in no way affects, the first search in no way affected you other than the time it took to do it, right?
Yes.
Right, because you've only got one dictionary in front of you, you can only search one word at a time. So the first word search delayed the second word search. Plus the remaining 999,999,998 other words. Okay, so you sit there and you flick through the book a billion times, and eventually you've finished spell checking your billion word file. So if instead we run that on our computer, it'll run a little bit better than doing it by hand, because the computer can hopefully bring the whole dictionary into memory, or at least some indexes that let it dig through the document very quickly. But your computer will still spell check your document one word at a time. Okay, and that's because the limit is probably going to be the disk drive on your computer, which is probably where the dictionary is stored. It has to keep going out and getting pieces of the dictionary depending on where it's at to actually see, is this correctly spelled? But there's a cheat that can be done. You may know that most people have a very limited vocabulary, right? Probably under 10,000 words. Most people use less than 1,000 words in any given day, right? So it turns out you can just bring in the 2,000 or the 10,000 most common words out of a dictionary of 100,000 words, and that much more trivial dictionary can sit in memory, right? And you only have to go search the rest of the dictionary when you can't match it across the 10,000 most common words. Okay, there's a word for that. It's called caching. Have you ever heard of that term before?
Yes.
Okay, so that's what caching is. Caching is being smart about not of finding the stuff that you need most often and making that easily available, right? And so computers do that. All computers these days have caching for memory,
Yeah.
right? The dictionary example is a higher level version of the same thing. It's doing a cache at the program level rather than the program running level. Okay, so that's how a computer does a spell check, right? You start off with a dumb algorithm, right?
Yeah.
An algorithm is a high-tech word for the formula, right? I use the term algorithm because I like to sound like I know what I'm talking about. So there's an algorithm for how you search a dictionary, right? If it has tabs, then you can, jump to the right tab and then dig in, right? And so I could teach someone that the act of me teaching someone how to use a dictionary would be the dictionary search algorithm, right? Look for the right tab, then start searching within, and then you could suggest things like how do you start in the middle of that section and then move left or right? I mean, there's a term for that as well. It's called a binary search, where you keep splitting what's left in half each time. Are you familiar with that term?
No.
Okay, let me teach it to you because it's worth it just for understanding how computers are used to solve problems. I'm going to think of a number from 1 to 100. What's your first guess?
88.
Bad guess.
Oh.
It's a bad guess because you didn't split the problem in half. The best guess is 50.
50.
Right? Because so if you pick 80 something and I say it's lower, you've still got 80% of the problem in front of you. Right? There was a 20% chance that you'd have 20%, right? Everything above.
Yeah.
But there's just, right, for your first guess, right? The best guess is 50 because it guarantees that you've split the problem in half.
I have a background in professional gambling, and these kind of games are very popular there. And the way they approach is that the people pick lucky numbers a lot.
Right. So the assumption for my game that I'm screwing with you on is that the number I pick is totally random. Right?
Sure.
So if you ask 1,000 people to pick a number from 1 to 100, it turns out it'll cluster around certain numbers. Right? Some of it'll be random because they actually did a random number, but there'll probably be 50 answers, which is the number 7, or something like that. Right? Probably 0 gets a lot of hits, 100 gets a lot of hits, right? But if it was truly random, the best guess is 50, right? And I'll then tell you that the number is below 50, right? What's your second guess?
25.
Good for you, right? Excellent second guess. It's above 25. So we won't play the rest of the game, but you should see that there is a guaranteed maximum number of guesses that it will take to get from not knowing what the number is to the right number. Because if you keep splitting the number space in half each time, you will get to the point where, right, so the answer is it's 7 guesses. Within 7 guesses, you can always, 8 guesses, you can always get the number, right? If you actually 1 to 100, sorry, it is 7, right? 7 is actually the correct number all the way up to the range 0 to 127, right? As soon as you get to 128, then the worst it'll take is 8 guesses, and that's true all the way up to 255, which is, look, this is getting too detailed, but the point is there is an algorithm for finding something, and that algorithm happens to be called a binary search because it keeps splitting it in half, which is binary, right? And computers are really good, but that's also the way you do a dictionary search, right? You open the dictionary, if you didn't have tabs, you open the dictionary in the middle, and is your first letter before or after that middle word. And then you look at the pages and you split that in half and you do it again, right? And so actually the optimal way to do a dictionary search, right, is a binary search.
Right.
Or if you're lucky, you have an index, right? So for instance, you could mark 100 pages of your dictionary, right? Like every 100th page, pick the word in the top left corner.
Yeah.
And now you have a list of 100 words. Do a binary search on that list of words without even opening the dictionary. And that then tells you where to open the dictionary, and you've cut the problem down by a factor of 100. Okay, so that's our dictionary search on a normal computer. There are tricks we can do, like caching the most common words.
Mm-hmm.
There's also the trick of having an index, which lets us cut the dictionary up into 100 separate dictionaries, right, of equal size, right? And just knowing what the first and last word is of each one. Okay. Nevertheless, your computer can only test one word at a time, because inherently your computer is serial, right, in doing what it's doing. Okay. But there was an opportunity there on your normal computer, if you have multiple cores, that the initial part of the search, right, maybe splitting it into 100 pieces, right, that could be done in parallel on each core, right? Because remember, the characteristic of a dictionary search is every word that you're testing, every word you're trying to check, is independent of all the other billion words you're trying to check, right? So whenever you see a workload where you can split the thing into things that can run totally independently, now you've got an opportunity to take advantage of all those cores that your processor has.
Mm-hmm.
Okay, so the limit then is, if you've got a 16-core processor, the limit is you can probably spell check, or at least do the front end part of the spell check, not 16 times faster on a per word basis. Each word takes just as long as it used to take, but you can now do 16 words in parallel, right? So you can't do the final part of the spell check in parallel, but you can do the front end part. And if you've got enough memory, maybe you have 16 copies of those 10,000 words, one for each core, or maybe you've got a computer that lets you share that cached area, and all the cores can share that cache, right? And so all 16 cores of your processor could go look at them separately. Okay. All right. So what about FPGAs?
Yeah.
So when we talk about that search, it's still very serial on a per word basis, and each core cannot start on the next word until it's finished with the current word it's dealing with, right? So the 16 cores can each start on working on a word independently, but they can't each start on whatever their next word is until they finish working on that word.
Okay.
Right? So in some fixed amount of time, you get 16 spell checked words per cycle. Okay. Over on an FPGA, we can take a very complex calculation, which, let's say we have a calculation where we have batches of numbers that come in 100 at a time, and we want to calculate the average, right? So if you try to do that on a normal computer, you can basically cycle around 100 times, adding the numbers to the sum, and at the end you divide by 100, right? Pretty easy calculation. We've all done it from primary school onwards. And then you get another batch of 100 numbers, and you have to do it all over again, right? And to put this into perspective, I'm talking about AI training. I know it didn't sound like I'm talking about AI training, but I am, right? You take a bunch of numbers and you do a bunch of calculations and you get an answer that says yes or no and is part of the training process, right? And then you take a new data set and you do the same thing again. Here's where the FPGA is totally different from anything else. In the FPGA, you get to build a custom computer that takes all 100 input values all at once. And it then adds the first two numbers together in parallel with the third and fourth, in parallel with the fifth and sixth, right? And in fact, it takes all the pairs of numbers, because it doesn't matter what order you add numbers together, the result is the same. So if you could do 50 add operations, you could go from 100 values down to 50 values in one operation. You can then go from 50 answers down to 25 answers in another one operation. And if we keep doing that, you'll find that by the time we do 7 parallel operations, I will have the answer to adding 100 numbers. So I went from 100 numbers down to a total sum in only 7 operation cycles, because I was able to parallelize all 50 initial adds, right? So it's a totally different way of looking at your data. Instead of taking them one at a time, you take all 100 at once and do all the adds you can do with 100 numbers, right? Which is take them 2 at a time and deliver 50 results. And then you do it again and again and again. And so if you were drawing a diagram with 100 numbers across the top, you'd draw 50 adders, 50 add operations, and you'd show 50 results. And then you draw 25 adders that take those 50 results 2 at a time and deliver 25 results. So you end up with this tree type structure if you draw it out on paper. The FPGA lets you build that custom computer, right? And here's the real magic. Those operations each take the same amount of time, right? The time it takes you